In the previous video we have shown that the total angular momentum I should say, can be written as this, and here we assume that we have a reference frame that is attached to the system and the center of mass is fixed with respect to the origin, and very often what we do is simply say, well, the center of mass and the origin coincide, right? If the reference frame is attached to the system, this means that the position vector, okay, to each particle I is fixed, okay, relative to the system. Okay, so this velocity vector cannot have any translational component as I is fixed. So the velocity must come from rotational motion. Okay, this is why we can write the velocity like this, like we have seen before. So we're going to inject this one in the formula of the total angular momentum, and we obtain this thing here. So how do we go from here to here? We have seen at the beginning of the course, we have reviewed, I haven't shown it, that the triple product, cross product C is equal to B times scalar product of C minus C, the scalar product of A and B. If you use that, you obtain this thing here, which you can rewrite to this thing, and finally to this quantity over here. Okay, we've rewritten the total angular momentum like this, right? And now we are going to write just the x component of this total angular momentum. Don't forget, this is a vector, and the x component will just call it Lx. So the vector Ri, it has components xi, yi, and z or zi, right? And the angular rotation vector has components omega x, omega y, and omega z, right? So I've made a drawing. You have your mass, mi, it's the mass of element or particle I. It has a position vector Ri with coordinates xi, yi and zi, right? They are shown over here. And then you can take the scalar product of Ri times itself, right? And the scalar product of omega, the rotation vector, the angular rotation vector, times the position vector, and this is what you obtain. So if we take the x component, omega has x component omega x, so we'll have this one times omega x. Where do you find this? Well, it's this thing here times omega x, right? The x component of this one will give you x I, and then you have to multiply with this thing here. So it will give you a term in wxxy square, wxxy square with the minus sign, that's okay. with the mass in front, and you'll have something with wy, xi, yi, it's this one here, and a similar term like this one, right? Now we are going to use this scalar product. What comes in here is ri square minus xi square. So if this one goes on the other side, you see that it's equal to yi squared plus zi squared. This is how we go from here to here. And this one we'll call jxx, this one we'll call jxy, and this one we'll call jxz. Okay, and you can do something similar for the y component of L and the z component of L. Well, we've done everything in detail for the x component of L, L being the total angular momentum. You can do the same thing for the y component and z component, and this is what you obtain, right? Here you see that you can write things differently, and you can rewrite it in kind of a nice notation where you have again the total angular momentum. Here you have the angular velocity vector, and you have here an what is called inertia matrix. It's often called like that. Well, we've seen that we can write the total angular moment as j times the angular velocity vector, right? The diagonal elements are given by these elements, or you can write them differently, okay? And they are actually moment of inertia coefficients, right? The off-diagonal elements are called products of inertia. So in this formula, you have to read this equation as an operator j acting on a vector to produce a new vector. Often you see the name inertia matrix, but you should actually say inertia tensor matrix, right? And this is this j element here. So what you see here above is for systems of particles. You can do something similar for continuous bodies. Summation has to be replaced by volume integration, and of course you have to use density. These are things that you have been doing in other courses. Okay, we've just seen that the total angular momentum is equal to j times the angular velocity vector, right? And in general, this matrix, this inertia matrix, is not diagonal. We've seen in the linear algebra course that we can actually make a matrix diagonal. It's an eigenvalue eigenvector problem. Okay, remember that in S you put the eigenvectors of the matrix J and you stack them in columns, and if you do this calculation you'll end up with an inertia matrix that is diagonal. Okay, this means that you are, instead of working in this system of reference XYZ, you go to a new system of reference X prime, Y prime, Z prime by doing a coordinate change, and this is the coordinate change, right? And then this coordinate change frame, sorry, you can write that the total angular momentum expressed in this new frame is JD times the angular velocity vector in this new frame, with the advantage that this is diagonal. Okay, so this is a big advantage. So very often we choose a set of body axes, okay, where the inertia matrix is diagonal, okay, and these are called principal axes. Let's take the example of a rugby ball or a spheroid. If you take these axes, x, y, and z, these are the principal axes, and if you take the inertia matrix in this reference frame, you'll have a diagonal matrix, right? If you take your axes at random, suppose they are at the same origin, then you'll end up with an inertia matrix which is not diagonal. So we're about to arrive at our conclusions. We arrived at rigid body dynamics, which studies the movement of systems that are interconnected under the action of external forces. They are rigid in the sense that they do not deform under the action of the applied forces, right? So it can be defined as a system of particles, right? So either an finite amount of particles or an infinite amount of particles, so a continuous system. But the fact is that the distance between the particles is fixed and cannot vary with time, okay? If we attach a reference frame to the body, then the analysis of the dynamics reduces to the analysis of translation and rotation. So now we can wrap up and kind of conclude. So what we saw is that in an inertial reference frame, the variation or the time derivative of the total angular moment in this inertial frame is equal to the net torque. Right? So this is the first result. So we've seen also that this is something that is not related to rigid body dynamics. It's a general result. You can link a time derivative in an inertial frame to a time derivative in a rotating frame. Remember, we have already used this for the velocity vector and for the acceleration vector, for instance, when we have seen the different fictitious forces, Coriolis force, etc., etc., right? So now I'm applying the same formula, but to the derivative of the total angular momentum. Derivative in the inertial frame, derivative in the rotating frame, and then I have to account for the fact that the rotating frame is rotating, and this is actually giving you an additional term, which is always the angular velocity vector cross product with the vector of which you're taking the time derivative, right? So this gives us our first equation, second equation, right? So we've just seen that in a rotating frame that is attached to the system, right, and very often we'll say that the origin of the frame lies at the center of mass, then we have this result here, is that the total angular moment in the rotating frame is J, this is our inertia matrix, times the angular velocity vector. You can do and derive the derivative in the rotating frame, and you'll have a derivative appearing here, a derivative appearing here. This one we'll write this way, and this is then the angular acceleration vector, the derivative of the angular velocity, right? This is equation 3. So equation 3 will put it in equation 2 over there, and we know that this one here is equals to tau. So let me find some place. So we know that J times alpha, the vector alpha, plus omega cross product with L is equal to tau. And this is what is called Euler's law of motion for rigid bodies, and it's motion in rotation. In the previous slide I had left Euler's equation with L written here, L being the total angular momentum, but of course the total angular momentum, we've seen that you can write it as the inertia matrix times the angular velocity, right? So this is the final version of what is called Euler's equation of motion. So this is the general form, but now we'll have a look at what happens if you have a reference frame that is attached to the object. Very often, as I said, the center of mass will be the origin of the frame, but often you have a tendency to use a reference frame which is built on the principal axis, and in this case J becomes a diagonal matrix, right? So let's see how we can see how things evolve when J becomes a diagonal matrix. Okay, remember Euler's equation. Yeah, so we have tau is J alpha plus omega cross J omega. So this is Euler's equation. Okay, so we're going to take a J that becomes a JD. So this thing here, which is L, simplifies simply because the matrix is diagonal. Okay, so J omega becomes very simple. You can write it like this, and now you need to compute this cross product that is over here. You can do that using this determinant, and if you do the calculations, remember that you're specialists in calculating determinants. You obtain the following equation, and it has components in x, y, and z. Okay, so this is again Euler's equation. We make the assumption that J is a diagonal matrix. So what we'll have here is simply J times the acceleration vector in rotation, well, which is also linked of course to the derivative of the angular rotation vector. But since J is now diagonal, this thing here, you can write it component by component, and it will only give this contribution for component x, for example. This is linked to component x. Okay, so of course here I have tau x, and in the previous slide I have calculated this thing here, and I've written it as a vector with component x, y, and z, and this is the x component of this thing here, right? X component. So these are Euler equations in the case of a diagonal matrix, and here they are in an expanded form, right? Now we can have a look if the axis of rotation points in the z direction, right? So this means that the vector omega is simply 0 omega z. Okay, so this means that alpha is 0 omega z dot, right? So if you inject that in this set of equations, because of the fact that these ones are 0, you get this thing here. Okay, and this is the result that we had found previously for a particle in planar rotation, right? So this is the moment of inertia times the acceleration vector in rotation is equal to the net torque. Okay, let's make a summary. If you have a rigid body, yeah, you can describe its motion in translation and in rotation. Yeah, this equation here, it's second law of Newton. Mass times acceleration vector is the net force applied on this object, on this rigid body, but you have to take into account that it's written for the center of mass of the object. This equation here that describes the motion of the rigid body in rotation is described completely as rotational motion of the body around its center of mass. Okay, so center of mass here is crucial, and the things that are appearing in here, it's the net torque, the inertia matrix, it's appearing 2 times, the acceleration vector, and the angular velocity vector that is appearing 2 times. Okay, as we have seen in the previous slides, if the inertia matrix becomes diagonal, there is this expanded version of Euler's law of motion that is often used, and we will use it also to model our quadcopter. For the orientation of the rigid body, we'll use 3 rigid body frames. The inertial frame, this is of course the well-known frame that is attached to the surface of the earth and has some its origin at some fixed point. Then there will be the local frame. It has the same orientation as the inertial frame, but it's attached to the center of mass of the body. Okay, so this is the center of mass of the body. And then you have the body fixed frame, right? This one is fixed to the center of mass, but it has the same orientation as the inertial frame. This one, this body fixed frame, is attached to the body at the center of mass and moves with the body, right? So we can use, for instance, the local frame for everything that has to do with the trajectory of the center of mass, right? This is what is shown here by the blue line with arrow. And then everything that has to do with rotation, change of attitude, will be described by going from the local frame to the body fixed frame. Okay, as I said before, any general displacement of a rigid body can be represented as translation and rotation, right? So translation of the center of mass with velocity vector v. This is what it was shown in the previous slide with this blue line with arrow. And then rotation around the center of mass around the angular velocity vector omega. And to describe the motion of a rigid body, we need 6 coordinates, right? We need 3 Cartesian coordinates to describe everything that has to do with translational motion, right? And we need 3 coordinates for the rotational motion, right? And you can either use Euler angles, right, or Tait-Bryan angles. Okay, Tait-Bryan angles you might know under another name, yaw, pitch, row, and this will be used for our quadcopter model, right? The Euler angles are described in the slides, but you will see they are marked for your information only, so they will not be covered in this presentation. So if you want to describe the motion of a rigid body in free space, and we will do that for our quadcopter, you see that there are 6 degrees of freedoms, and there will be 6 equations of motion, 3 in translation and 3 in rotation, right? And here I will stick to my Tait-Bryan angles for everything that has to do with rotation, which is called also attitude. And there are 3 variables to describe, well, translational movements, right? So the 3 variables for translation is forward, backward, left, right, up and down, kind of logical, right? Then you have orientation. Yeah, we'll start with yaw. This is this one here. Pitch, and roll. We'll use this concept when we'll make our model of the quadcopter. Okay, so as you can see, I have skipped quite a few slides concerning the Euler angles, right? In this presentation, in this video presentation, I will stick to the Tait-Bryan angles. They are used by mostly pilots, US and British pilots, to go from the local frame to the body frame. And it's just a question of convention, right? They do this in a sequence. First there is a rotation which is called yaw around the z-axis, then there is a rotation which is called pitch around the y-axis, and then there is a third rotation which is called roll around the x-axis. So the transformation from the local frame to the body frame is done in 3 steps. So there is a first counterclockwise rotation of the angle phi around the z-axis of the local frame, right? Afterwards, you have a counterclockwise rotation of theta around the new. When you rotate with the angle phi, you have a new axis here, system, and you have a new y-axis. And in the second step, you rotate with theta around the eta axis. Now you produce a new set of reference axis, and in the last step you rotate by a counterclockwise rotation of psi around this new x-axis, right? And this generates the body frame. Phi, theta and psi are yaw, pitch, rho. Okay, so if you start from any configuration in the local framework, you can go to any configuration in the body frame, right? And you use 3 Tait-Bryan angles, as I've said, phi, theta and psi, and they are denoted yaw, pitch, rho. So what is important here is that we first rotated around the original z-axis in the local frame, then we rotated around the new y-axis in the new reference frame, and then we've rotated around the new x-axis, right? So we have a kind of convention here that we have used z, y prime, x prime. Okay, the order is z, y, x, right? This is this order of sequence, right? So this is a convention. If you look in the literature, you will see that there are other conventions that are used. For instance, sometimes they are using, instead of counterclockwise, clockwise rotations, and sometimes the order of the sequence here is changed, right? So you have to be very careful if you open a book or something, or a publication, and you see Tait-Bryan angles, if they're using the same sequence order, and if rotations are clockwise or counterclockwise. What can be said is that the definition that is used here in this slide is the one that you see most often. Okay, what you see here is the original local frame. Okay, and to remember you, we're using this z, y prime, x double prime sequence. So the first thing that happens is a rotation around the z-axis, and phi here is actually the yaw parameter. Then you turn around the new y-axis, which is eta. This is what is called pitch. Theta is the pitch variable. And then you turn around the new x variable, and this is the rho variable psi. Okay. Okay, remember that you go from the local frame to the body frame through 3 rotations, right? You start from the position vector in the local frame, and then you do a rotation around the z-axis, it's d. Then you do a rotation around the y-axis, see it here, and then finally a rotation around the new x-axis. Okay, so if you multiply b, c and d, you obtain a matrix A, and very often I'll write L to B, meaning local to body transformation, right? And if you do this kind of calculation, b times c times d, you obtain A. We know that this matrix is orthogonal, this matrix is orthogonal, this matrix is orthogonal. So if you take the product, you'll have a matrix A which is orthogonal. This means that if you have to go from the body frame to the local frame, okay, so it's the inverse transform. The nice thing about a orthogonal matrix, and you know that since you had a very good course on linear algebra, is that instead of taking the inverse, you can simply take the transpose. Okay, so A transpose is the transformation from body to local frame. Yeah, in this slide you see that of course you don't have to do this multiplication b times c times d by hand. You can simply do that using MATLAB and the symbolic toolbox, and it will do the calculations instantly. Okay, so this is the result of the previous slide and how it has been computed. Okay, to explain this slide I will have to go forward and backward in the slide, so my apologies for that. The idea here is that I want to express the angular velocity vector omega here in terms of the derivatives of the Tait-Bryan angles. I have velocities here, or speeds, yeah, so I need derivatives of the Tait-Bryan angles. We know that we go from local frame to body frame to, through 3 successive Tait-Bryan rotations, and we'll assume that these rotations are infinitesimal. We've seen at the beginning of the course that 3 successive infinitesimal rotations, they can simply be added, right? This is what I'm doing here, and this of course will correspond to a rotation around the vector, the angular velocity vector, right? So the 3 successive Tait-Bryan rotations are a first rotation around the original z local axis, then a rotation around the new y-axis, and it's denoted eta, and then finally a rotation around the new x-axis, which is already the body axis, yaw, pitch, rho. Okay, and since we have here angular velocity, well, you have here derivatives of the angles corresponding to yaw, pitch, and rho. This is expressed in body coordinates, in local coordinates, and in one intermediate coordinate. So I would like to express my angular velocity vector in terms of the body coordinates, right? This one is already in the body coordinates, so I don't have to do anything, but now I have to express this vector, and the unit vector after a certain number of operations, and it's the new y vector, and the unit vector in the original local frame in the z direction. Well, I would like to bring them to the body coordinates, right? So I have to do some kind of transformations. Here you can already see that to go from this one to body coordinates I have to use the transformation B, and for this one I'll have to use the transformation A. And now I want to show you that this is indeed the case. So let's return to my animation here, and let's go forward. This is yaw, this is D, pitch, C matrix, yeah, and this is rho, this is the B matrix. Okay, so you see that to go from eta to the which is the y-axis in the intermediate coordinate system to yb, you need to do a rotation with the last matrix, which is the B matrix, right? And to transform the z-axis here in the local frame to the z-axis in the body frame, well, you do need to do all 3 transformations, right? To go from this one to this one, you simply need to do the product of the 3 matrices, and this is using the A matrix. Okay, so you can transform this one through the A matrix to the body coordinates, and you can transform this one to the body coordinates through B. Now it's simply multiplying A by a vector 0, 0, 1, and B by a vector 0, 1, 0. So here it will be selecting the last column of A, and here it will be selecting the second column of B. Let's have a look. Last column of A, this is indeed what we saw on this slide, and the second column of B, right? And these are indeed the results that I see over here. Okay, we've seen that we've used infinitesimal rotations, 3 of them, okay, and since they are infinitesimal, they add up, and they add up to the angular velocity vector omega. Well, we want to express this omega in terms of the body frame. This one is already in the body frame, and we have seen in the previous slide that it's possible to express the z component in the local frame in terms of the body frame. Here it's written, and you could do this same thing for this y component of this intermediate reference frame, and you can also express it in terms of the body frame, right? So now if you plug that in here, you have omega expressed in the body frame, right? And this gives these equations, right? Let's do maybe the first equation, and then I'll leave you the remaining equation. So you take the first component, the x component of this one here. Well, you have 2 terms that will give you a contribution. This one will not give you a contribution because there's nothing here, right? This one will give a contribution. Yeah, it's c dot, here it is. And this one will give you a contribution. It's this one times minus sine theta. You can do the same exercise for the other 2 equations, and now we have the relation between the angular velocity vector and the derivative of the Tait-Bryan variables. This is the rotation vector omega here expressed in the body axis. You can do a similar exercise and express it in the local axis. I have not done that because this is the one that we'll be using for our quadcopter model. Okay, I've written the preceding equation in matrix form, right? So this is your angular velocity vector. It's linked to the derivatives of the Tait-Bryan variables. Okay, psi, theta, phi, yaw, pitch, rho. Okay, and sometimes I want the relation to be the other way around. So I would like to be able to write the derivatives of the Tait-Bryan angles knowing the xyz components of the omega vector. Of course, then you have to invert the relation, and straightforward calculations give you this thing here. Okay, and these calculations are straightforward if you again use the symbolic toolbox of MATLAB. It's just a question of minutes, right?